is the Module 13 SAS video. So as always, we want to start out with our folder where we've got all of our information. So some piece of information you want to make sure you have handy are the code book. You want to have the Module 13 SAS Word document with the notes, as well as the Module 13 SAS script. Alright, so we're going to start out by looking at the Module 13 notes. So in this module, we're going to look at how to perform some hypothesis tests using SAS. Now, one thing to keep in mind, we're only going to look at a select few hypothesis tests here for the BRFSS dataset. There are many, many more that are possible. So the first one we're going to look at is how can I use SAS to perform a one sample proportion z-test? And so the question is, at the 5% significance level, is the percentage of people living in Kentucky during the year 2018 receiving a flu vaccine less than 50%? And so notice here in our research question, I've included that 5% significance level, and the reason we want to make sure we include that is acknowledging our uncertainty in the process. There's always the possibility that a hypothesis test makes the wrong decision, and so we need to include that significance level, which acknowledges the potential for that error. So using the 2018 BRFSS data, we can test this hypothesis, so let's see how to do that. So I've opened up my SAS code here in SAS, and remember the very first thing we always have to do is to import our data set. So the first thing I'm going to do is change the location. And I'm going to run this. And I need to change my file name from this computer and the one I normally work on. So I need to do KY. This needs to be, here we go. I'm going to try running that again. All right, everything looks good now. So let's see how to do this one proportion z-test. So this is going to look very similar to the single proportion confidence interval that we looked at in Module 12. And so the very first thing, whenever I'm working with any of my variables, is I want to make sure I explore that variable a little bit and I have an understanding of how it was coded. So I'm going to run my frequency table. So here's my frequency table. And so I see that for the Kentucky data set, flu shot took the values 1, 2, and 7. So I'm going to go to my code book and see what those represent. And I've actually already got flu shot pulled up. So notice the value of 1 represents a yes, 2 is a no, 7 is a don't know or not sure. And then for the Kentucky data set, I have no refusals. For your data set, you may have some refusals. And then next we can go straight into performing the hypothesis test. And what you're going to find here is this is very similar to when you constructed the confidence interval. The only difference is I've tacked a little bit more on here in the code. So let's run this. All right, so we still have that output where we saw the confidence interval, but before we ignore this, but notice we have this piece of information here. And what this does is this gives us our test statistic, our Z, as well as our one-sided p-value. And notice we do have a one-sided test here because we're testing to see if that proportion is less than 50%. Now going back to the code, notice here I put in p equals 0.5. The reason for this is we were checking to see if less than 50% did something. Most of the time you're probably going to be comparing to 50%, but you might not be. You might want to be comparing to something else. In that case, you can put in whatever value you want there as long as it's restricted between 0 and 1 because proportions are restricted between 0 and 1. Going back to our notes, notice I copied over that relevant piece of output so that you could see it and highlighted the piece that we need. I made a data note here. Notice here we're considering the proportion of those responding no, don't know, or refused as the complement of the yes. So we always want to say, yes was what we were interested in, and then what everything else was. So for this example, since that p-value is less than 0.05, at the 5% significance level, we have evidence that less than half of Kentuckians received a flu vaccine in the year 2018. Right? Now, it could be that, oh, and actually let me go back up here. One of the things I didn't talk about here, that I should have is whenever performing a hypothesis test, we always have to make sure that we met our assumptions. So let's go back to our output. Notice here when we looked at our original table, remember that for our assumptions we do need a random sample and we need those sample size requirements. Well, we've obviously met our sample size requirements here, so we were fine to use that test. But there will be times that you might have smaller sample sizes and that assumption is violated. When that is the case, you can use an alternative hypothesis, which is the binomial exact test. And so I'm going to show you how to do that. So we're going to pretend that we violated our sample size assumption, and so we couldn't use that 1 proportion z test. So instead we would need the binomial exact test. Going to our SAS code. Again, we would use a table to make sure we understood how a variable was coded and to get a feel what's happening with that variable. And then to perform the actual exact hypothesis test, we add in this exact binomial line. So running this, right, notice it has added in down here an extra piece, which is the exact test. And so I have copied that over. So for the exact test, we would use this p-value. Notice using the exact test, it's still significant. So at the 5% significance level, we have evidence that less than half of Kentuckians received a flu vaccine in the year 2018. The next test we're going to look at is a hypothesis test for a difference in proportions. So a potential research question here could be, at the 5% significance level, is there a difference in the proportion of people living in Kentucky with good, better health who received the flu vaccine compared to the proportion of people living in Kentucky with fair, poor health who received the flu vaccine during the year 2018? So again, we're going to use our data set and SAS. So going over to SAS here. All right, so first thing as always, I'm going to make a contingency table of my variables to make sure I understand what is happening with those variables. So here is my contingency table. Again, I see that flu shot takes 3 different values, yeses, nos, and then the don't knows. And then for my health variable, I've got 1, 2, and 9. And so if you'll recall from previously, the 1 is the better good, the 2 is the fair poor, and then the 9s are the refusals. All right, for that, going back to the SAS code. All right, so what we need to do, and this is exactly what we did when we worked with the confidence intervals, is we need to take that data and create a contingency table, or in other words, we summarize it in a 2x2. So I'm creating a new data set here, and I'm calling it flu_health. And what I'm going to do in this case is I'm going to group the don't knows and the refusals and the no's into one group and compare those to the yeses. And so this is exactly what we did when we looked at the confidence intervals. So then to perform the hypothesis test, I actually again run the same code as I did with the confidence intervals, except I'm going to add in this risk diff equal to. So let's run this. And notice here we have this risk difference test. This is what's going to perform that test for the difference between the two. And it gives us some different values here. The one that we're interested in is the z and the two-sided z. Because notice here we're testing for a difference in the proportion, so we're looking to see if they're not equal to one another. So here is our p-value. So looking back at our document here. Oh, I realize that I have a mistake. We don't have this one highlighted. Let me change that. So here is our test statistic and our p-value. So again, notice our p-value is less than our significance level. So here we can say at the 5% significance level, we have enough evidence to prove the percentage of people living in Kentucky with good, better health who received the flu vaccine differs from the proportion of people living in Kentucky with fair, poor health who received the flu vaccine during the year 2018. The last hypothesis test we're going to look at is the chi-square test of independence for 2 dichotomous variables. So here we could ask the question, is there sufficient evidence at the alpha equal 0.05 level to conclude that a person's health status is not independent of whether or not they receive a flu vaccine? So again, we can use the data to help us. Here I have a contingency table just like we saw before. Now I'm going to do something a little bit different this time. I need to summarize my data here, but what we're going to do is for health status, I want to make it a dichotomous variable. And so how I'm going to do that is I'm going to store health as either good or other. And then for flu vaccine, I want that to be a dichotomous variable as well. So I'm going to store it either as yes or other. And so notice the others in either case are going to also include the don't knows and the refuse to answers. So based off the contingency table that we get from running this code right here, I can build myself a new smaller data set, just like we did with the confidence intervals. And so I can run this, and notice I've called it flu health 2. And then I can run the hypothesis test just like we did before, but the only difference here is I'm going to now include chi-square because I want to perform the chi-square test. So let's run this. Notice here is my new results. Now you'll notice it says statistics for the table. There are several different hypothesis tests that are actually run here. And so the one that we are going to use is the continuity adjusted chi-squared, which is this one right here. For majority of the tests that you run, or I shouldn't say majority, but many of them will have an optional different types of corrections that account for different things. For this particular test, there's what's called a Yates continuity correction. Some softwares recommend that you always use the continuity corrected. There are other articles out there that say not to use the continuity correction, that it's too restrictive. The discretion or the choice of which one to use is often up to the researcher, and the important thing is you want to justify whatever you do. So for this illustration, I am going to use the one with the continuity correction, but if you go back to the code, notice I've included a link right here. You can read more about the Yates correction at that link. Right, so if we go back to our notes, notice I have the output here and highlighted, and so our conclusion is at the 5% significance level, we have enough evidence to conclude that a person's health status is not independent of whether or not they receive a flu vaccine. Going back to our SAS notes, now another option is instead of focusing on yes, other, and good, better health and other, instead of the other category, we could have just focused on the no's, and that would have also been valid. So in other words, what we're going to do is set all of the refusals and the don't knows to missing. And so what I've done here is, again, using my contingency table, I have figured out what those totals should be if I don't count the refused answers and the don't knows. And so here's what my new table would be. So notice I've called it flu health 3. And then I could run the exact same code, just calling flu health 3 to run that test. Whether you group the don't knows and the refusals into your analysis, or you consider those missing, that is up to you as the person running the analysis. The important thing, though, is to document what you do and make it very clear, this is how I ran the analysis. So if someone else were to come, and look at this data or look at your results after you, they know exactly how you got those results and they could reproduce them. And this is what we call, reproducibility, and it's very important. So either way you choose to run that analysis is valid, but you have to document what you want to do, or what you did do. So this is going to conclude the Module 13 SAS video. As always, this is just enough to get you started. For example, one thing that you might notice here is I did not show you the test of associations when you have nominal variables with more than 2 levels. Well, to do that, you would do exactly what you did here, except you would just have more levels than 2, but the code is very similar. So as you're working through your data set, as always, if you have questions or you come across something you want to do and you're not sure how to do it, just ask me and I'm more than happy to help you.